Okay.
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 Good afternoon and welcome to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Nurlan Ismailov from the Astana IT University. The title of his talk is On a Variety of Right-Symmetric Algebras. Please.
Okay, thank you. Good afternoon, good evening. I'd like to first thank organizers of this seminar for opportunity to give a talk here. So my title is On a Variety of Right-Symmetric Algebras. It is the results on this talk based on joint work with Professor Umirbaev. So short content of my talk is the following. So first, I will recall what the Specht problem is and what kind of varieties this problem considered and solved, and then I will talk about varieties of right-symmetric algebras, and then I briefly talk about Specht problem for varieties of Novikov algebras. These results based on our joint work with Professors Vladimir Datsenko and Umirbaev. And then finally, in more details, I will talk about Specht problem for right-symmetric algebras. So what is the Specht problem or finite basis problem? So let V be a variety of algebras, and we say that it's finitely based, or it has a finite basis of its polynomial identities, if our variety can be defined by a finite system of polynomial identities. Otherwise, we say that it is infinitely based. And we say that our variety of algebras has a Specht property, or Spechten. In some case we say satisfies Specht property if any of its subvarieties has a finite base of identities. So Specht in 1950 formulated this problem, the following problem. He asked that is every variety of associative algebras of the field of characteristic 0 finitely based? So this is the classical Specht problem. So this problem also studied not only for associative algebras, but also for non-associative algebras and so on. So first here, I'd like to give some simple examples. So for example, if we consider matrices, 2x2 matrices, and then consider over the field of characteristic 0. So we know that it satisfies the standard identity of degree 4, for example, this one, right? And it's known that matrix algebra, 2x2 matrix algebra, satisfy this identity, so-called whole identity. So here, by this, I mean a commutator of elements x and y. And it's known that Drensky in 1981 proved that all identities are consequences of these two identities. Of course, here we also consider associativity. And so, namely, variety of associative algebras generated by 2x2 matrices satisfy the Specht property. Okay. And one example for infinite base of identities, for example, if I consider here, if you consider here 5-dimensional algebra with this multiplication table, okay, so here we are given this multiplication table, and all other products are equal to 0, then it's easy to see that it's not associative. And in 1977, Parfionov and Maltsev proved that this algebra has infinite base of identities. So this algebra satisfies following identities. Okay, and Fn for any n, it's not the consequence of previous these two identities and previous polynomials when n is lower, right? And this is one example, simple example of an algebra that has infinite base of identities. So here, some well-known examples. So this question was considered for variety of Lie algebras. Von Lie in 1970 proved that of the field of characteristic 2, he constructed a four-dimensional algebra that has no finite base of identities. And then this result was extended by Drensky in 1974, and he proved that this result remains true for any characteristics. And Ilyakov, 1992, he proved that any variety of Lie algebras generated by finite dimensional Lie algebra of the field of characteristics 0, it has a Specht property. But this question still remains open when, for example, if you consider variety of all the algebras of the field of characteristics 0, it's open question. Okay. And this problem also considered for Metabelian algebras. Medvedev, he proved that varieties of Metabelian Maltsev algebras, Jordan algebras, alternative algebras, -1 algebras are all Spechten. And then Umirbaev, 1984, proved that variety of Metabelian binary Lie algebras over a field of characteristic not equal to 3 has the Specht property. And Belkin, 1976, he proved that variety of Metabelian right alternative algebras doesn't satisfy Specht property. Lvov constructed six-dimensional non-associative algebras that satisfies this identity, x, y, z equals 0, and it has infinite base of identities. And Isaev, using Lvov's method, he adapted his method and adapted for right alternative algebras, and he constructed finite dimensional Metabelian right alternative algebras over any field, and he proved that it has infinite base of identities. And Kuzmin, 2008, gave a sufficient condition for varieties of Metabelian right alternative algebras of the field of characteristic not equal to 2 that becomes Spechter. And for alternative algebras, this question considered by Umirbaev, and he proved that varieties of solvable alternative algebras of the field of characteristic different from 2 and 3, it has Specht property. And Pchelinsev in 2000 constructed an almost Spechten variety of alternative algebras of the field of characteristic 3. By almost Spechten, it means the variety itself, it is not Spechten, so it has no finite base of identities, but any of its subvariety, proper subvariety, is Spechten. And Specht problem for associative algebras, it was solved by Kemer in 1988, and he proved that variety of associative algebras over the field of characteristic 0 has finite base of identities. But for positive characteristics, it has negative answer. This question, many counterexamples constructed by Belov, Grishin, and Shigolov. For bicommutative algebras, this question was solved by Drensky and Jakhaev, and they proved that a variety of bicommutative algebras over any field satisfy the Specht property. So this is the short history of Specht problem for varieties of algebras. Okay, now our main object in this talk, it is right-symmetric algebras. So we say that algebra is right-symmetric if it satisfies the following identity. So here, ABC, it is associator, which is defined like this, and it is equal to ACB. So here we see that two right variables are symmetric, BC and C, that's why it's called right-symmetric algebras. So here we consider a variety of right-symmetric algebras. And it's known that it is this variety is from this variety we can obtain Lie algebras under the commutator. Right? So here well-known example for right-symmetric algebras is the following. So if we consider polynomial algebras over the complex numbers in variables x1 and x2 and so on, and then we consider with algebras. So with algebras, it's the Lie algebra of all derivations of polynomial algebra. And we know that it is this algebra has this kind of basis. And we define multiplication, new multiplication by this way. And one can easily check that this algebra with respect to our circle product, it becomes a right-symmetric algebra. So here we have following known results about variety of right-symmetric algebras. First, it was considered by Cayley. He considered realization of these algebras in terms of rooted trees. And 1994, the base of right-symmetric algebra was constructed by Segel, and there are also other two different bases, which were given by Chapaton and Livernet. And there are also another basis given by Jumla-Didaev in terms of rooted trees. And Philippe proved that any nearly right-symmetric algebra of the field of characteristic zero is right-nilpotent. And Khozubayev and Umirbaev proved that in 2004, they proved analog of PBW basis theorem for the universal multiplicative enveloping algebra of right-symmetric algebra. And the combinatoric properties of a variety of right-symmetric algebras considered by Khozubayev, Makar-Limanov, and Umirbaev, they proved that Frese's theorem is true. Frese's theorem valid for right-symmetric algebras. And recently, it was proved that variety of right-symmetric algebras over the field of characteristic zero is Nielsen-Schreier. So it was proved by Datsek and Umirbaev. So they proved that if we consider a free right-symmetric algebra, if you take its any subalgebra, it's always free. There is one important subclass of right-symmetric algebras. It is called Novikov algebra. So Novikov algebra, it is a right-symmetric algebra with this identity. So A, B, C. Here we have left commutativity and BAC. Okay. So if we consider here with algebra of index n, when n equals 1, we can see that W1, it is a Novikov algebra. But n is greater than 1, it's not Novikov, it is just right-symmetrical. So Novikov algebra, it's also a well-known class of algebras, which was first appeared in the paper by Gelfand and Dorfman when they studied Hamiltonian operators in the formal calculus of variations. And it was also then rediscovered by Balinsky and Novikov in the context of classification of linear Poisson brackets of hydrodynamical type. So we proved that here every Novikov algebra, if it satisfies some non-trivial polynomial identity over the field of characteristic zero, is always it is right associated nilpotent. Okay, and we were able to prove that a variety of Novikov algebras over the field of characteristic zero, it has the Specht property. Okay, now we consider Specht problem for right-symmetric algebras. Okay, Now, now we consider here a variety. Here I denote it by beautiful R, which is defined by these three identities. So here commutator, ABC, and the AB, A is equal to 0, and the mutable identity. This is the variety defined by these three identities. And let A be an algebra from this variety. And we define here left and right multiplications as follows. So ARX, it is a product by right hand side, and LX is a product by multiplication by left hand side. And also we here consider operator VXY, which is defined like this, so LX and RY. So then using this our polynomial identities, we can obtain following relations of operators. Okay, Vx is 0 and so on. So it is alternative with respect to x and y. And here we have very nice relations among our operators. And using these relations, we can prove that every algebra of the variety R is right-symmetric, and it is right nilpotent of index 4. Okay, it is a subvariety of right-symmetric, a variety of right-symmetric algebras. Okay, now we construct finite dimensional right-symmetric algebra. Here we denote it by Pn. So for each natural number n, here we define algebra with bases EIG, BIG, CI, DIG, EIG, and here I and j, any number from 1 to n, and here the multiplication table is defined as follows. Here AIG, CI, DI, and so on. And here we define the following subspaces. AN, it is a subspace spanned by vectors AIG and BIG, and DN, it is CI, BG, and so on. And it's not difficult to see that AN, it is the subalgebra of our algebra Pn, and DN, it is ideal of Pn. And moreover, we can have this kind of very beautiful relations, this kind of relations between these our subspaces. So here, Pn can be written as a product, as a direct union of these our subalgebras. Okay, so then using that relations, we can easily show that our algebra Pn, it is it is an algebra that belongs to our variety R. And here also we have this kind of relation. So if our operator Vxy acts on our subalgebra An and Cn with this overline, then it gives us always 0. Okay, and here Vdy and Vyd is equal to 0 if y is any element of our algebra, and d it is from from subalgebra Dn, which is generated by Di, Eig, and Ci. And left annihilator of our space is it coincides with space Cn. Okay, Cn, it is a subalgebra generated by vector Ci. Okay, now here we give the basis of free algebra of our variety. So let f of x, it is a free algebra of this variety generated by our countable set x. Okay, then here below we get a set of elements. If you consider this set of elements, so xi, and here we act by right multiplication or it might occur or it might not. And then we act by left multiplication. So it gives us a space of elements of degree 2 and 3. And here we consider all elements of this form. And we then get that all these elements form basis of our free algebra. Okay, free algebra of this variety. So here we have this kind of relations between the variables. Okay. Now let M by M we denote multiplication algebra of our free algebra, and by E0 we denote subalgebra of our multiplication algebra generated by all operators of this form pxi xg. Okay, and then we define our space E1 in this form, so we consider space of space generated by E0, and we act by left multiplication. By E2 we consider our space and acted by Rxi. Okay, and here we have E3, and by Rk we denote sum of these all spaces. Okay, so here act on Xi and sum of all our spaces. So then it's not difficult to see that our free algebra, it is a direct sum of our spaces Rk and all linear elements of degree less than or equal to 3. Okay. Then here we have a very important lemma, which is the following. So if we have some polynomial from our free algebra, and it is an identity of our finite dimensional algebra Pn when n is greater than or equal to 2, then f can be written as a sum of our polynomials f0, f1, f2, and f3, where fk is taken from our this space, and moreover, and each one fk will be an identity of our finite dimensional algebra. Okay, so here we have this kind of very important lemma that will be used in our next statements. And then following lemma is that if f is a polynomial of this space R0, okay, and if we know that it is an identity of our finite dimensional algebra of this form, then we get that xm plus 1, so gi, it is an operator. If it acts on any variable, then it gives us identity of our finite dimensional algebra Pn. Next lemma, if we have some polynomial from R1 plus R3, okay, and then if we multiply it by xm plus 1, so by any variable, then it gives us some polynomial of the form R0 and R2. Okay, and if this is equal to 0 for our 0 in our algebra, then we can get that f will be the identity of our finite dimensional algebra Pn. Okay. Okay, so here I give the definition of partial linearization that is very well known. That so by delta it is a linear mapping that by acting on polynomials we can get partial linearization of our polynomials. So here I just skip the definitions. So this is well-known operator. Then we have the following lemma. So if suppose that our f is a polynomial of this form, so space from space R2, then if we act on f by this kind of operator. Okay, so we substitute for any I in our f, and by this variable xn plus 1, by this monomial, I would say, then it gives us a polynomial in R0. Okay, and moreover, if f is an identity of Pn, if and only if Pn satisfies the following system of identities. Okay, if we see that this is an identity of Pn, then we get that it is possible if if and only if this is the polynomial identities of our finite dimensional. Okay, now next, if f is some polynomial, so there exists this amount of polynomials gi from our E0, such that our f is an identity of Pn, if and only if Pn satisfies the system of this system of identities of this form. Okay. So here we have Tm number of polynomials from E0. Okay. Now let B is an algebra from our variety, and by E0 of P we denote algebra of operators generated by V, VB1, B2, where B1 and B2 are taken from our algebra B. And these operators act on our algebra B. By T of E0 of P, we denote ideal of E0, defined as intersection of all the kernels of all possible homomorphisms from our free algebra to algebra B. Then we can establish that if we consider this algebra is isomorphic to matrix algebra, algebra of n by n matrices. Okay. So from this isomorphism, we can, using this isomorphism, we will prove a very important lemma. It is the following. So if our algebra Pn has a finite basis of identities, when n is greater than or equal to 2, then ideal is generated by polynomials of bounded degrees. So now we start studying the identities of algebra P2. First we prove that there exists some algebra from our varieties with some certain properties. So for any s is greater than 5, there always exists an algebra B with following two properties. So first property is algebra B is generated by set Q with s plus 3 elements, such that ideal of E0 of P2 is not subset of ideal of E0 of P. Okay, and then there is some subalgebra C. So sorry, let C be a subalgebra of B generated by any subset Q prime of Q with S elements. Then our polynomials, if we consider this product, it is always equal to 0 for all polynomials from our T. So here by T, I mean this. And all the elements are taken from our subalgebra of P. So here we prove that we show that this kind of algebra always exists in this variety. So construction of this algebra is the following. So how do we construct that algebra? So first we said that n equals s minus 5. So so that n is greater than equal to 1. And H is a free algebra with identity in the variety of algebras generated by our field F, with free generators H1 and so on Hn. And let W be a subspace of H, spanned by all words in H1 and Hn, including the identity, but it doesn't contain at least one Hi. Then we consider an algebra A as a tensor product of H and P3. Okay. And we consider subalgebra of A, here we denote it by L, which is generated by this set of elements. Okay. A1, tensor product C1, and so on. So here we have Hi, so I here runs from 1 to n. And then we consider algebra n, which is defined as follows. So here H multiplied by tensor by C3, and here n prime, it is W tensor product C3. So it's not difficult to show that these algebras are ideals of L. Then if we define B as L factorized by n prime, then we prove that this algebra satisfies our two properties that we mentioned above. Okay. Then we consider this lemma. So let sigma be a set of generators of our ideal T of E0. Then for any natural number S, there exists a polynomial Fs from this set of generators that depends on more than S variables. Okay. So if we prove this one, then this previous this lemma, we can get that Pn has infinite base of identities. So in order to prove this lemma, here we use our algebra. In our proof, we will use our algebra B. So here below, I give steps of our proof. So first, we suppose that sigma consists of all polynomials that depend on variables no more than S, and then we assume that B is an algebra that satisfies our given properties 1 and 2, and then we consider epimorphism from our free algebra to algebra B. Tau here tau is defined as follows. Then this epimorphism induces from E0 to E0 of B. Okay, so if we define like this, we can get epimorphism from our spaces. Okay, and then if G is a generator, then by our assumption K is less than equal to S, and Ci is equal to T of Xi, and this will be belong to our subalgebra of B generated by S elements. Okay, so by property 2, we can get that this polynomial is equal to 0. Okay, and it means that G belongs to kernel of tau prime, tau tilde, sorry. So then if it implies that Kertau contains all our generators of polynomials, and consequently it contains our T. Okay, and then we take consider polynomial f on m variables from T. For any B1 and Bm from our algebra, there exists Ri from our free algebra such that Bi is equal to T of Ri for all i's. Since it is our ideal, then we can write this polynomial as follows, right? So here f belongs in T, that's why it is equal to 0. So it means that this ideal is contained in this ideal, so which contradicts our property 1. So by this way, we can get a proof of our lemma. So then we get that our algebra, finite dimension algebra P2, of an arbitrary field, it doesn't have finite base of identities. Okay, and from that we get that variety of right-symmetric algebras of an arbitrary field doesn't have the Specht property. So these results were published in these 2 articles. So result about Specht property for Novikov algebras. It was obtained in this paper, and Specht property for right-symmetric algebras was obtained in this paper. Thank you for your attention. If you have any questions.
Okay, thank you very much for your talk. Are there any questions, comments, or remarks? There is a comment on the chat. Florin Nikita is asking on page 7 an example.
Page 7.
Or
This is page 7,
right?
Okay. Yes. Okay. This is yeah. He proved he considered 6-dimensional algebra that satisfies this identity, and he proved that it has no infinite base of identities. What is the question?
He's asking for an example, but okay.
An example, please. From his proof, in fact, one can easily construct an explicit algebra. So what he I can't really remember that multiplication table, but that algebra, in fact, was given in his paper. But so he considered an algebra. So he splits that algebra into 2 parts. So first,
he considered
it is
a
a
specific
subspace.
6-dimensional non-associative algebra, and showed that it has no any. Okay.
Yes. So he takes a 2-dimensional vector space and consider space of linear operators that affect acts on this vector space. So, but I don't remember exactly the multiplication table, but it was given in his paper.
Yeah, it just showed that this algebra has no finite basis of identities.
Yeah.
Okay, any other question? I don't see any questions. So in this case, let's thank Nurlan again.
Thank you.
And we will resume on next Monday at the usual time. Thank you. Bye-bye.
Thank you.